Have you ever felt that relentless pressure, to become well-informed and fast? You're staring at just piles of articles, maybe research papers, notes, images, even codes
Oh,
sometimes.
absolutely. And the clock's always ticking, right?
Exactly. The sheer volume can just be overwhelming. It feels almost impossible to get a real handle on anything deeply without drowning.
It's a huge challenge. How do you cut through all that noise?
Yeah. How do we grasp complex topics without spending like days buried in information? It's something everyone faces, I think. So let's try and unpack this today. We're diving deep into a really fascinating paper, Jina-embeddings-v4, Universal Embeddings for Multilingual Retrieval.
And this isn't just another small step, is it?
Not at all.
Okay.
It's a huge 3.8 billion parameter multimodal embedding model from Jina AI, and it genuinely promises to change how we interact with information.
Right.
Our mission for this deep dive, then, is to explore how this Jina-embeddings-v4 model aims to be, well, a kind of shortcut to being truly well-informed across all sorts of data.
Bridging those gaps that have traditionally really stumped AI models and us.
Exactly. Especially how it tries to unify text and image understanding. That's the really exciting part for me.
And what's truly striking is just the sheer ambition here. It's designed as this incredible generalist, but also really precise.
How does it manage both?
Well, it supports both single vector and multi-vector embeddings. That dual approach gives you incredible flexibility.
Flexibility for different tasks, you mean?
Yeah, exactly. From really broad searches across massive data sets to super precise, nuanced retrieval of specific bits of information. And it's got particular strength, they say, in handling what they call visually rich content.
Visually rich content. So like documents packed with charts and tables.
Precisely. Charts, tables, diagrams, mixed media stuff. And it works across a really diverse range of retrieval scenarios, too. It's their big push, towards a truly unified understanding for AI.
Where an image of a chart is understood just as deeply as a paragraph of text.
That's the goal, a single, coherent understanding.
Okay, to really appreciate what Jina-embeddings-v4 is doing, we probably need to back up a bit. Let's talk about embeddings. What are they at their core?
Right, the fundamentals.
Right.
Imagine taking any piece of digital information, a word, a sentence, a whole paper, an image,
Okay.
and transforming it into a string of numbers, a vector.
Just random numbers.
No, not at all. That's the key. Think of it like assigning very precise coordinates to every concept, every idea, every visual element. It's like mapping everything onto this huge, high-dimensional digital map.
A map of meaning.
In a way, yes. And the magic is that similar concepts, say a photo of a cat and the actual word cat, get mapped to locations that are incredibly close together on this map.
And unrelated things.
They end up far apart. This closeness is usually measured using something called cosine similarity.
Cosine similarity. That sounds mathematical.
It is, but the concept is simple. It basically tells you how similar the direction of two of these numerical vectors is. If they point in roughly the same direction, the original concepts are semantically related.
Got it. So aligned directions mean related ideas.
Exactly. And that's the foundation. It allows AI to understand these incredibly complex relationships and meanings within vast amounts of data, even across different formats like text and images.
That makes sense.
Yeah.
But you mentioned challenges earlier. What were the traditional problems?
Well, traditionally, embedding models were pretty siloed. You had models built just for text, separate ones for images, maybe even different ones for audio.
Right, specialized tools.
Specialized, yes, but getting them to actually speak the same language, that's been incredibly difficult. For a long time, multimodal models tried to project things from different modalities.
Like the picture of a cat and the word cat.
Into the same semantic space, yeah. But they often suffered from what researchers call a modality gap.
A modality gap. What does that mean exactly?
It means that even things that are semantically related across modalities, the picture and the word cat, were still significantly further apart on that map than even unrelated items of the same modality.
Wait, so the picture of a cat might be closer to a picture of a dog than the word cat.
Counterintuitive, isn't it?
Yeah.
But yes, if the gap was wide enough, that fundamentally limited the AI's ability to truly connect diverse information coherently. Cross-modal search just wasn't as effective as we needed it to be.
Okay, so that brings us back to Jina-embeddings-v4. How does it tackle this gap?
It's designed specifically to overcome it. It aims to be a true generalist. Meaning it's a single base model that delivers competitive performance across the board. As a text embedder, an image embedder, and crucially as a cross-modal embedder, it bridges that gap.
That sounds like a massive shift.
Yeah.
So for someone like an analyst trying to understand market trends,
Yeah, imagine that scenario. You've got dense financial reports text, competitor ad campaigns images, internal meeting notes, more text.
before you'd be juggling different tools, right?
Exactly. A text search tool, an image analysis tool, maybe something else trying to stitch it together. And often the connections felt weak.
But with Jina-Embeddings-v4,
It's like having one AI assistant that just natively understands all of it, instantly. You ask a question, and it pulls insights from a table in the report, a visual element in an ad, and a quote from the notes, all seamlessly.
that's not just faster access. That's
Sure.
that's a different level of understanding.
It really is. It's informational synergy. It saves hours of manual cross-referencing and cuts down information overload dramatically.
And the single model approach must have practical benefits too.
Huge savings. Compared to deploying and maintaining multiple specialized AI models, this is much simpler. Less computational overhead, a more streamlined workflow for you, the user. Faster, more efficient access to understanding.
Okay, let's dive into the specifics from the paper. What do they list as their key contributions? This sounds really ambitious.
It is, and the paper lays it out clearly. First, there's this unified multitask learning paradigm.
Unified multitask learning. So not just training text and image models separately and sticking them together.
Precisely. It jointly optimizes the embeddings for both text and images right from the start, building that shared understanding from the ground up. And it supports both single and multi-vector outputs simultaneously.
Like teaching someone English and Spanish at the same time, but making sure they know cat and gato are the same concept and relate to the picture.
That's a great analogy. That deep shared understanding is foundational. Second, building on their previous work with Jina-embeddings-v4, they've incorporated LoRA extensions.
LoRA, Low-Rank Adaptation.
Right.
I've heard of that. It's about adapting big models efficiently.
Exactly. It's revolutionary. Imagine your base model is this giant knowledgeable brain.
Okay.
Now you want it to become an expert in, say, legal documents or medical research or even code. Instead of retraining that entire colossal brain, which is incredibly expensive and slow,
You attach a small expert module.
that's LoRA. It adds only a tiny fraction of the parameters. Here, just 60 million per adapter, less than 2% of the total model memory footprint.
Wow. So you get specialized performance without the massive cost.
That's the idea. They can achieve results comparable to huge, specialized models across diverse tasks, query-based retrieval, semantic similarity, code search without needing entirely new models. It's incredibly efficient specialization.
It's impressive. What else?
The third major contribution, and this is huge for real-world documents, is its prowess with visually rich content.
Right, we touched on this. Beyond simple image captions.
Way beyond. The paper highlights significant progress with materials that mix text and images, complex tables, intricate charts, diagrams, mixed media layouts. It actually outperforms other multimodal models significantly on these.
So better than models focused just on OCR or basic Q&A on documents.
Yes, better. Existing benchmarks like VDR often stick to those simpler tasks. Jina-embeddings-v4 supports a much more diverse set of uses for these complex documents. It's not just reading the text, it's understanding the visual context and the data within the image.
Okay, that makes sense. If you have a model that's good at complex visuals, you need a way to test it properly.
Exactly. Which leads to their fourth contribution, the Jina-VDR benchmark.
A new benchmark.
Yes, a novel, publicly released benchmark specifically for screenshot retrieval and visually complex documents. It's multilingual and multi-domain.
Going beyond those existing benchmarks like VDOR.
Absolutely. It expands the scope significantly. Multilingual retrieval, wider variety of query types, diverse materials, academic papers, maps, ads, manuals. It's designed to test models on the messy, complex data we actually encounter.
So the benchmark itself is a contribution to the field.
Definitely. It provides a much-needed, comprehensive evaluation tool for this space.
Okay, this all sounds amazing, but how?
Yeah.
How did they actually build something this versatile? Let's pull back the curtain, look under the hood.
Right, the architecture. This is where the clever decisions really come in. It starts with the
Right.
foundation, the Qwen 2.5 VL model.
Qwen 2.5 VL, that's the backbone.
Exactly. Jina-embeddings-v4 uses that as its core, inheriting its ability to process both text and image inputs from the get-go.
And it's a big model.
Oh yeah, 3.8 billion parameters in the backbone,
Look-
plus about 60 million for each LoRA adapter on top.
Wow, what about input sizes?
It can handle really long text inputs up to 32,768 tokens. Think entire books or long legal contracts. And images get resized to a hefty 20 megapixels, keeping lots of visual detail.
So a powerful foundation to build on.
Definitely. That backbone gives it the inherent multimodal capability right from the start.
Now, you mentioned something earlier about a single processing path for text and images. That sounds really different from older methods.
It is. That's one of the most interesting architectural choices. Think about older models, like CLIP-style dual encoders.
Right, they had separate models for text and images.
Yeah, one expert for text, a different one for images. They worked independently, and then during training, you'd try to align their outputs, get them to coordinate their understanding later.
Like teaching two people different languages and hoping they can translate accurately between themselves.
A good way to put it. It works, but it's not seamless. Jina-embeddings-v4 does something fundamentally different.
How so?
Its image embedding model isn't just making a standalone embedding, it acts as a preprocessor for the main language model.
A preprocessor. How does that work?
It takes the image and converts it into a sequence of vectorized image tokens.
Image tokens, like visual words.
Sort of. Think of it like super advanced OCR, but instead of just text, it extracts semantic chunks of the image, chart region, table data, logo, face.
Sure.
These aren't just generic features, they're structured so they can be fed directly into the LLM.
As if they were text tokens.
Exactly. The LLM processes the visual words and the actual text words in one single unified stream.
So you can pass in text and an image together in one go.
Yes, making it truly multimodal in a single input field. And this isn't just neat, it gives performance advantages. The model understands the relationship between visuals and text much more holistically right from the start.
A single universal language for all data types. That's powerful.
It really is. And that brings us to the outputs. Because input is one thing, but how it delivers the results is also key. It offers dual mode output for flexibility.
Dual mode. Okay, what are the options?
First, you have single vector or dense embeddings, the more traditional kind.
One vector represents the whole input.
Yep, whether it's text or an image. The default size is 2048 dimensions. But the key feature here is they're truncatable.
Truncatable, you can make them smaller.
Exactly. Down to as little as 128 dimensions with minimal precision loss.
How is that possible? Minimal loss.
It's thanks to something called Matryoshka Representational Learning, MRL.
Matryoshka.
Yeah.
Like the Russian nesting dolls.
Precisely. Each smaller doll still represents the core concept, just with less detail. Here, the embedding dimensions are roughly ordered by semantic importance, so chopping off the less important ones doesn't hurt the core meaning much.
That sounds incredibly useful for balancing precision and efficiency.
It really is. You could use the full 2048 dimensions on a server, then truncate to 128 for a mobile app or edge device. For these, they just apply mean pooling to the final layer to get that single vector.
Okay, so that's single vector. What's the other option?
The second option is multivector, or late interaction embedding.
Multivector. So not pooled.
Right. It keeps individual vectors for each token in the input, including those image tokens we talked about.
How big are those?
There are 128 dimensions per token. So the total output length varies depending on the input length.
And this is like models such as Colbert.
Exactly. Comparable to Colbert or Colpoly, known for high-precision retrieval, these are meant for late interaction comparison strategies.
Late interaction.
Yeah.
Meaning you compare the token sequences, not just the single summary vectors.
Yes. Instead of comparing two summaries, you're comparing all the little pieces. Imagine comparing two detailed blueprints. You check how each small part of one relates to any part of the other.
Finding all the hidden connections.
That's the idea. The similarity calculation is specific too, not just simple cosine similarity. It sums the maximum similarity of each query token to any document token. It's more granular.
But I assume this is more computationally expensive.
Significantly.
Yeah.
More storage needed, more compute for the comparison, but it's generally more precise, especially for complex or long inputs. So you get to choose precision or efficiency.
That flexibility is key. But with the LoRA adapters for specialization, is there a risk it becomes a jack of all trades, master of none? Or do you really get specialized performance without compromise?
That's a really important question, and LoRA is designed precisely to avoid that problem.
How?
Remember, LoRA lets you adapt the huge base model for specific tasks by adding just a tiny number of new parameters, only 60 million per adapter here.
Right, less than 2% of the total size.
So you don't fine-tune the whole 3.8 billion parameters for every task. You just load a small, lightweight adapter that subtly tweaks how the base model applies its knowledge for that specific purpose.
Like putting special glasses classes on the expert brain.
Exactly. The core knowledge is there, but the focus sharpens dramatically. And users can select these adapters at inference time, switching between specializations on the fly.
And they all still handle images and text.
Yes, all three maintain that multimodal capability. Let's break them down. First, the asymmetric query document retrieval adapter. This is for when your query is different from a document, like a short question or keywords.
So it encodes the query and document differently.
Precisely. To improve accuracy when searching a long report with a short question like what causes climate change, it understands the difference in structure.
Makes sense. What's the second one?
The semantic similarity and symmetric retrieval adapter. This is for finding truly comparable content.
Where the query and document have a similar structure or goal.
Right, like finding paragraphs or images explaining the same medical procedure, regardless of wording or format. It's about finding semantic equivalence.
And the third?
The code retrieval adapter. Highly specialized for programming tasks.
Like asking in English for Python code.
Exactly. Natural language to code, code-code similarity, technical Q&A about code. It shows the versatility extends even to structured data like programming languages.
So you get near state-of-the-art performance in each area without needing 3 separate giant models. That really addresses the jack-of-all-trades concern.
It does. It's efficient, targeted specialization.
Okay, that's impressive specialization. But it leads to the next big question. How on earth do you train something this versatile? Handling different modalities, different tasks, and doing it efficiently.
That's where their meticulous two-phase training process comes in. And crucially, before they start, the model weights are initialized from Qwen 2.5 VL Instruct. So it starts with a strong, pre-trained foundation.
But they don't retrain that whole foundation.
No, and this is key for efficiency. The core backbone weights are frozen. They only train the LoRA adapters and a multi-vector projection layer.
So the adapters learn how to modify the backbone's output for specific tasks?
Exactly. It allows specialization without the massive cost of full fine-tuning. Super smart.
Okay, so phase 1, what's the goal there?
Phase 1 lays the groundwork. It builds the fundamental multimodal understanding. It starts with a contrastive objective.
Contrastive, teaching it related versus unrelated.
Yep. Inputs are classified as related or unrelated. The model learns to embed related things close together and push unrelated things far apart, like a sophisticated sorting game.
And how does it learn across text and images simultaneously?
Through dual batch sampling. In each step, they use 2 batches, one with just text pairs, btext, and one with multimodal pairs text, plus a related image, bmulti.
So it learns within text, within images, via those image tokens, and across text and images all at once.
Correct. Like teaching a kid dog with pictures, words, and descriptions simultaneously.
Clever. How do they measure success during this phase?
They use a unified loss function, based on InfoNC's loss, for both single and multi-vector outputs. InfoNC pushes positive pairs closer than negative pairs.
But you have single and multi-vector outputs. Don't they behave differently?
They do. And that's where Kullback-Leibler divergence, DKL, comes in. Think of it like balancing the training for a sprinter and a long-distance runner in the same race. DKL compensates for differences in how errors distribute between the 2 output types. It stops one from distorting the training of the other, ensuring both improve effectively.
And you mentioned Matryoshka loss earlier.
Yes, applied in both phases. That's the secret sauce, ensuring the single vector embeddings are truncatable. You can peel layers off without losing the core meaning.
Wow. What kind of data did they use for this general training? Must have been massive.
It was. Text, and text-image pairs from over 300 distinct sources. A huge curated collection.
And the text-image pairs weren't just simple captions.
No, they describe the curation as eclectic, far beyond cat sitting on a mat. It included website screenshots, rendered markdown files, complex charts, dense tables, basically materials found in the wild.
So real-world, messy documents right from the start.
Exactly. Plus diverse queries, questions, keywords, phrases, long descriptions, facts. This builds that broad, nuanced understanding needed for a truly universal model.
Okay, so phase 1 builds the foundation. What happens in phase 2?
Phase 2 is where it gets its specialized skills, using those LoRA adapters. They take the general adapter trained in phase 1 and make 3 copies.
And train each copy for a specific task.
Precisely. Each copy gets specific, targeted training using distinct data and loss functions tailored for its specialization. Highly efficient.
Like giving that brilliant intern 3 intensive master classes.
Good analogy. So let's look at the asymmetric retrieval adapter training first.
Okay, the one for short queries, long documents.
Right. Its goal is distinct embeddings for queries and documents. They use a prefix method, adding like query or passage to the input so the model knows what it's seeing.
And the training data
Very sophisticated. It uses hard negatives,
are negative.
triplets, a query, the correct document, and a document that's semantically related but wrong. This forces the model to make really fine distinctions.
Learning to spot the subtle differences.
Exactly. They use datasets like WikiSS, the multilingual VDR, plus mine hard negatives, and an expended info in C plus loss function to handle these tricky examples effectively. Pushes it to be super precise.
Okay, what about the text matching adapter, the one for semantic similarity?
Its purpose is finding comparable content, symmetric tasks. So the training relies more on ground truth. Similarity values human judgments of how similar texts are.
How does that work in the loss function?
They mainly use the cosent loss function. It takes two pairs of texts with known similarity scores and pushes their embeddings together or apart based on those scores.
But there isn't that much data with reliable human similarity scores, is there?
True. So they augment that ground truth data from datasets like STS12 and 6E with other pairs that don't have known similarity, using standard info and C loss for those, a blend of precise supervision and broader contrastive learning.
Smart. And finally, the code adapter.
Right. For natural language to code to code, technical Q&A, obviously the vision part isn't really involved here.
Did the base model already know some code?
Yes. The Qwen 2.5 Zail backbone had some inherent code understanding from its pre-training on things like Stack Exchange QA and Code Search Net. That gave it a head start.
And the LoRA training.
Similar to the asymmetric adapter using triplets, query, correct code, related but incorrect code, mine from code-specific sources like Code Search Net, Code Feedback, APPS programming problems, and the huge Cornstack dataset.
So highly specialized training, even for technical domains like code. Incredible versatility.
It really demonstrates the power of the LoRA approach.
Okay, that's a seriously thorough training process. But it brings up a critical point. How do you even measure if a model this versatile is any good? Existing benchmarks sound inadequate.
They often are. Benchmarks like VDR or MIEB are useful, but narrow. They focus a lot on basic OCR, simple question answering on visual documents.
Right. Can it read the text? Can it answer a direct question about the chart?
Exactly. But they don't capture the full complexity of real-world retrieval across modalities, languages, diverse document types, and different kinds of user queries. They lack diversity.
So you need a better yardstick.
Absolutely essential. And that's precisely why Jina-VDR was created.
The new benchmark they introduced, what makes it different?
It's specifically designed to evaluate performance across the full spectrum of visually rich document retrieval. It integrates textual and visual understanding of documents as rendered images, charts, tables, text, the works.
How does it expand on something like VDR?
Significantly, it adds 30 new tasks, spanning diverse domains, legal, historic, marketing, scientific. Diverse materials, charts, tables, manuals, maps, printed text. Diverse query types, not just questions, but facts, descriptions, context searches. And crucially, it's deeply multilingual.
Multilingual across how many languages?
Some datasets span up to 20 languages. It's designed to test seamless operation across languages. And it's compatible with VDOR, using LLM filtering for query relevance. Includes non-question queries, too, like matching GitHub descriptions to rendered Markdown images.
It really sounds like it mirrors real-world complexity.
That's the goal, a benchmark fit for purpose.
And how do they build this benchmark? It sounds like a massive undertaking itself.
It was, and quite resourcefully done. They started by repurposing existing datasets.
Taking old datasets and giving them new life.
Exactly. They took VQA and OCR datasets like Donut VQA, Table VQA, and used structured templates plus generative LLMs to create new, rich text queries that match the visual textural content. Some, like JDoc-QAJP and Hungarian DoQA, needed minimal changes.
What about non-conventional formats?
They tackled those too. Our World in Data used encyclopedia fragments as queries for charts. GitHub Redmire Retrieval used rendered Markdown from real readings with generated descriptions in 17 languages.
17 languages? Wow.
Yeah, really pushing the multilingual visual aspect.
Did they also create data manually?
Yes, manually annotated datasets were crucial for capturing real-world use cases and genuine information-seeking intent.
Like what?
Academic slides from Stanford lectures, educational figures, marking materials like the Jina AI yearbook, Japanese ramen guides, even the huge Shanghai master plan documents. Queries were carefully human-written to reflect how someone would actually search these. They also used existing human annotated sets like ChartQA.
So, a mix of repurposed and handcrafted data. What else?
To fill the remaining diversity gaps, especially where human annotation wasn't feasible, they used synthetic data generation.
Using AI to create benchmark data.
Exactly. For instance, getting historical or legal documents in German, French, Spanish, etc., and using Qwen2 to generate relevant queries. They did similar things for Hindi government VQA and Russian beverages, adding underrepresented languages and domains like public service docs or commercial catalogs.
Any other examples?
TweetStock Retrieval used chart data with multilingual template queries. Airbnb Retrieval used rendered tables with queries in 10 languages. They even synthesized bilingual examples, French-English, using advanced LLMs like Gemini 1.5 Pro and Claude 3.5 Sonnet, specifically to test cross-lingual performance.
That's incredibly comprehensive, using AI to build better tests for AI.
It really is an innovative approach to benchmark creation itself.
So with this robust benchmark, how did Jina-Embeddings-v4 actually perform overall?
The aggregate results in the paper, Table 3, show it consistently hitting state-of-the-art levels. It particularly dominates on both Jina-VDR and VDOR, especially in that high-precision multi-vector mode.
Which confirms that multi-vectorlet interaction generally gives better precision, right?
Exactly. It's known for higher precision, though it costs more computationally. The fact that Jina-V4 excels there, but also performs well in single-vector mode, highlights its capability and flexibility. It's setting new standards.
Let's break down that performance. Where does it really shine specifically?
Okay, in multilingual text retrieval, it generally beats its predecessor, Jina-Embeddings-v3, and is very competitive on standard benchmarks like MTE and MMTB.
But you mentioned long documents earlier.
Yes, this is where it gets really interesting. It dramatically improves on long document performance, shown on the long embed benchmark. It significantly outpaces most competitors there.
That's huge for anyone dealing with long reports, papers, legal docs.
Absolutely. Asking a question about page 300 of a PDF and actually getting the right answer? Yeah. Much more likely with this.
What about finding texts with similar meanings? Textual semantic similarity.
Highly competitive on MTB-STS and MMTB-STS benchmarks, and actually best in class for English similarity tasks. Exceptional nuance in understanding textual relationships.
So finding news articles with the same core message, for example.
It would be very adept at that, yeah.
And the big one, multimodal retrieval, linking text and images.
Higher average score than models like Jina-CLIP-V2 and NLOB-SIGLIP Large on the CLAP benchmark. And as we said, state-of-the-art on Jina-VDR.
And you mentioned it excels where others struggle.
Right, particularly on non-question-like queries in visually rich documents. Other models might handle direct questions okay, but Jina-V4 is better at understanding the context of, say, a GitHub description and matching it to the rendered markdown image, or finding a chart based on a description of its content.
Interpreting those complex visual textual relationships.
It's a massive leap.
And finally, code retrieval.
Competitive with general-purpose embedding models on MTB-Quar, while super specialized models like Voyage Code might still have a slight edge.
Its strong performance across all these diverse areas, including code, is the real story.
Exactly. It highlights its generalist strength and broad applicability.
Okay, let's circle back to something fundamental, that modality gap we talked about. You said the architecture helps minimize it. How does the paper actually show this?
It's fascinating, and they provide visual proof. Remember the gap. Similar things across modalities ending up further apart than unrelated things of the same modality, like text and images living in different neighborhoods on the map.
Right. Harder for the AI to connect them.
Figure 2 in the paper shows this beautifully. If you could see it, you'd notice for older models like OpenAI, CLAP, and Jina-CLIP-V2, the distributions of similarities for image-text pairs versus text-text pairs are quite separate. There's a visible gap.
A barrier between the neighbors.
Precisely. But then you look at the plot for Jina-Embeddings-v4, that gap is dramatically reduced. The distributions largely overlap. It's a much more unified, cohesive space.
And that's because of the shared encoder architecture.
Exactly. Sharing an encoder introduces this bias towards a shared region of the embedding space, Unlike separate encoders that tend to push modalities apart, the model inherently learns to think about text and images in the same conceptual space.
So can we measure this alignment, put a number on it?
Yes. Using the cross-modal alignment score, the average cosine similarity of matching image and text pairs. The results are striking.
What are the numbers?
Table 4 shows Jina-embeddings-v4 hitting 0.71 on Flickr 30K and 0.72 on MSOCO, OpenAI CLP. Only 0.15 and 0.14 respectively.
Wow, that's a huge difference.
It absolutely confirms Jina-V4 generates a far better aligned cross-modal embedding space. The picture of a dog and the text a dog are much, much closer semantically than in previous models. True integration.
You mentioned a nuance with CIFAR 100, though.
Right. Poorer alignment there, but the paper explains it's because CIFAR 100 labels are very simple, often single words, much less descriptive than the rich text in MSCO or Flick 30K. So the quality of the text impacts alignment. Makes sense.
It does. Now, beyond the modality gap, you mentioned another subtle challenge, the cone effect. What's that about?
Ah, yes, the cone effect. It's where contrastive loss can inadvertently cause matching cross-modal pairs to cluster in a sort of high-dimensional cone instead of spreading out evenly.
Like trying to stuff everything into a narrow funnel instead of using the whole space?
Exactly. It's an inefficient use of the embedding space, making it harder to precisely distinguish between similar and dissimilar items.
And is there visual evidence for this too?
There is in Figure 3. It compares the distribution of similarities for positive, correct versus negative, incorrect image-text matches.
What does it show?
For OpenAI CLP, the difference between correct and incorrect matches is small. Their distributions overlap a lot. Harder to tell them apart. Jina-Clip V2 is a bit better.
But Jina-embeddings-v4
shows a much greater spread. Very distinctly separate peaks for positive and negative pairs, meaning it uses much more of the embedding space effectively. This leads to greater overlap between image and text distributions overall, but far more precise differentiation between relevant and irrelevant pairs.
So practically speaking, more accurate search results, fewer false positives.
Exactly. Clearer distinctions between what you want and what you don't. It directly translates to better, more reliable results for you.
Okay, as we wrap up this deep dive on Jina-embeddings-v4, let's just quickly recap the journey.
It's been quite a ride through the tech.
It really has. We've seen its powerful multimodal and multilingual capabilities, unifying understanding across data types and languages in a really groundbreaking way.
That single processing path was key, turning images into image tokens for the LLM.
Absolutely. A novel approach, and the flexibility too, single vector for efficiency, multi-vector for precision. Choose your weapon.
Plus the LoRA adapters for that efficient specialization, asymmetric queries, semantic similarity, even code.
All without bloating the model, which is critical, and backed up by state-of-the-art performance, especially on those visually rich documents, validated by the new Jina-VDR benchmark.
And fundamentally, those architectural improvements, reducing the modality gap, mitigating the cone effect, lead to a more accurate, efficient embedding space.
It's not just technical, it's practical.
Absolutely. Connecting this to the bigger picture, this isn't just another small AI update. It feels like a significant step towards information retrieval being just fundamentally more intuitive, more precise.
Regardless of how the information looks or what language it's in.
Exactly. For you, the learner, that means real benefits right now. More accurate search, better understanding of complex documents with charts and figures, seamless integration of text and visuals in your research.
Getting to that well-informed state faster and with more confidence.
That's the promise. And looking ahead, they mentioned future plans enhancing multilingual capabilities even further, exploring smaller, more efficient variants.
Making these powerful tools even more accessible.
That seems to be the direction.
So let's leave everyone with this thought. Imagine a future where you genuinely never feel overwhelmed by a document, no matter how complex it looks, how many charts or images or languages it contains. What kind of new questions would you start asking if your tools truly understood everything you threw at them, whatever the format? What new connections might you make if the AI could instantly breach the gap between a dense visual and a complex paragraph across any language, giving you immediate insights? It's a provocative thought, isn't it? Thinking about what a truly universal understanding of data could unlock for learning and discovery.